SpaceX's Starship aims to make space travel as routine as air travel, revolutionizing how we think about journeys beyond Earth. The vision is to launch, land, and relaunch Starship with minimal downtime, just like commercial airplanes. And the key to this ambitious goal is full, rapid reusability, making it possible to fly to space, return, and prepare for the next mission in record time. The biggest technical challenge? The heat shield, Starship's only defense against the searing heat of re-entry at 17,000 miles per hour. As the spacecraft plunges back into Earth's atmosphere, temperatures soar to thousands of degrees, threatening to melt or destroy anything unprotected. Unlike single-use ablative shields that burn away with each flight, Starship's ceramic tile system must survive repeated, punishing re-entries with only minimal repair or replacement. This means the tiles need to be incredibly tough, reliable, and easy to maintain. This is what sets Starship apart from past vehicles like the Space Shuttle, which needed months of painstaking tile repairs after each mission, often delaying the next launch and driving up costs. SpaceX uses thousands of black hexagonal ceramic tiles to absorb and radiate heat, protecting the stainless steel body beneath. Each tile is carefully designed to fit together, minimizing gaps and maximizing protection. The steel's high melting point adds a crucial safety margin, making Starship more tolerant to tile loss or damage, a lesson learned from the tragic Columbia disaster, where a single damaged tile led to catastrophe. Every test flight is a step toward perfecting this critical reusable shield. Engineers analyze data, inspect tiles, and make improvements after each mission, inching closer to true rapid reusability. Without this breakthrough in thermal protection, the dream of affordable, frequent spaceflight remains out of reach. Starship's shield is not just a technical marvel, it's the gateway to a new era of space exploration. Starship's 10th flight in August 2025 marked a major milestone for SpaceX, featuring a precise splashdown, improved aerodynamic control, and most importantly, a brutal real-world test of the vehicle's heat shield under extreme conditions. This mission was closely watched by engineers and space enthusiasts alike, as it pushed the boundaries of what reusable spacecraft can endure during atmospheric re-entry. After re-entry, detailed images revealed a dramatic orange streak and several white patches scattered across the black heat shield tiles. These markings were clear evidence of the intense thermal stress the vehicle experienced as it plunged back through Earth's atmosphere at hypersonic speeds. Online speculation quickly erupted, with many suggesting a major tile failure. However, SpaceX confirmed that the vast majority of tiles remained firmly attached, an impressive improvement over previous flights and a testament to the team's ongoing refinements. Yet, the white patches pointed to a deeper, more subtle issue. Superheated plasma had managed to seep through tiny, almost invisible gaps between some tiles, eroding the secondary thermal barrier beneath and leaving telltale scars on the surface. Even the smallest seam or imperfection can act like a blowtorch during re-entry, channeling thousands of degrees of heat directly onto vulnerable areas of the spacecraft. While the main structure survived this ordeal, the heat leakage raised serious concerns about long-term reusability, and more critically, the safety of future crews who will rely on this system. Flight 10 made it clear that simply keeping the tiles attached isn't enough. The entire heat shield system must be perfectly sealed to prevent plasma intrusion and protect the spacecraft's integrity. The wealth of data and high-resolution images collected from this flight became the driving force behind the next round of design improvements, offering engineers invaluable insights into real-world performance. Addressing this gap heating problem quickly became SpaceX's top engineering priority, setting the stage for even safer and more reliable missions in the future. The orange streak on Starship after Flight 10 was no accident. It marked an experiment with metallic heat shield tiles. SpaceX hoped metal tiles might be tougher and easier to install than ceramics, but during re-entry the metal tiles oxidized heavily, turning orange and allowing heat to leak through. Post-flight analysis confirmed they failed to insulate as well as ceramics. The experiment was decisive, metallic tiles weren't the answer. For SpaceX, learning what doesn't work is as valuable as a breakthrough. The team quickly refocused on improving the ceramic tile system. The next challenge, stopping plasma from sneaking through the gaps. To fix the gap problem, SpaceX invented the crunch wrap, a thin, flexible, heat-resistant layer wrapped around each tile's edge before installation. Unlike NASA's old gap fillers, which often failed, the crunch wrap is integrated and designed for robotic assembly. When tiles are mounted, their wrapped edges press together, sealing out plasma. The material withstands re-entry heat and flexes with tile movement. This approach is simpler, more reliable, and scalable for rapid reuse. By automating the process, SpaceX avoids the labor-intensive inspections that slowed the shuttle. Flight 11 would be the crunch wrap's first real test. Starship's 11th flight, set for October 2025, is all about testing the crunch wrap, a new and innovative heat shield design that promises to revolutionize spacecraft re-entry. This test will evaluate the performance of the heat shield across the entire surface of the spacecraft, ensuring that every tile can withstand the extreme conditions of re-entry. Every tile will be meticulously wrapped, and the re-entry profile will be even harsher than any previous test, pushing the limits of the new design. The goal is clear: no white patches, no plasma erosion, and no signs of damage. This would mark a significant milestone in spacecraft durability. This is the final and most critical test for the V2 Starship design before SpaceX transitions to the larger and more advanced V3 model. The Super Heavy booster is also being reused for this mission, showcasing significant progress in rapid turnaround and reusability. If successful, Flight 11 will prove that SpaceX has overcome the biggest obstacle to achieving full reusability of their spacecraft. This breakthrough will unlock a new era of operational missions, including the deployment of next-generation Starlink satellites and in-orbit refueling for the Artemis missions, paving the way for deeper space exploration. The stakes couldn't be higher, as the success of this mission will set the stage for the future of space travel. Cracking the heat shield challenge transforms Starship from prototype to practical, world-changing spacecraft. Rapid reusability slashes costs and makes spaceflight accessible, shifting it from rare government projects to routine commercial operations. With a proven shield, Starship Vi-3 can launch bigger Starlink satellites, expanding global internet coverage. The Artemis program depends on Starship's quick turnaround for lunar missions. SpaceX's rapid, iterative approach, testing, learning, and improving with every flight, has redefined aerospace engineering. Each flight's data feeds the next breakthrough, accelerating progress. Solving the heat shield problem is the cornerstone of making humanity a multi-planetary species. Starship's success means the cosmos is finally within reach for all.